Okay.
Yep, we can see it.
Okay, thank you very much, Ryan. Appreciate it. Yes, it's been a difficult year last year for travel, i.e. none, except around the state. My goal today is to give you a arm-waving overview of the initiation of transgressive sheets and dunefields. And bear in mind, given some of the wonderful previous talks we've seen, this is very much arm-waving and a massive lack of data. Transgressive dunefields, just in terms of definition, broad aeolian sand deposits formed by normal oblique alongshore movement of sand over vegetated to semi-vegetated terrain, largely or partially unvegetated when active, and vary in size from relatively small sheets to quite large sand seas, on the scale of small desert dunefields. They transgress prior to rain. The definition is poor, but it's been around in Australia since, I guess, the 50s, and so we're kind of stuck with it. They tend to be defined into two types, and one is really like the sheets on your bed. They are rolling plains, largely without dunes or dunes without slip faces, according to the geological definitions. Whereas the dunefields, as you see in the photo here, tend to be dominated by various kinds of dunes, many of them similar to what you would find in deserts. They can be very extensive. For example, one of the largest in the world, one of the few you can see from space, is Lençóis Maranhenses in northern Brazil, an active dunefield 23 kilometers across, and the vegetated relic dunefields extend for about another 100 kilometers. So they can be absolutely massive. Here's a look at the middle of the flooded into dunes and barchanoid transverse dunes in Lençóis, for example. But they can be relatively small too. So, for example, this one's only 300 meters across or so, just south of Perth. It's more of a sheet than a dunefield at this phase, and some of the other typical landform units that we see in these dunefields are indicated here. This is the correct map of the world for those of you in the Northern Hemisphere. New Zealand's at the top. Notice if we ignore Antarctica, well, okay, Terra del Fuego is really at the top, but close. The arrows indicate where lots of the big coastal transgressive dunefields are in the world, and you'll see that they're dominated by the Southern Hemisphere, and that's because we have some of the largest waves, strongest winds, and high sediment supply. There are, of course, several on the European coasts, and the arid coasts along this part of the world are also well represented by transgressive dunefields, as is quite a lot of the West Coast and down to Baja, California, and Veracruz, and a few other places in South America, of course. Very extensive dunefields along the east coast of South America and the arid west coast of South America. So they occur in lots of different settings. They're very commonly large-scale, kind of tabular dunefields, as you see here with examples from South Africa, and again here. They quite often are headland bypass dunefields, which is they're just transgressive dunefields that are bypassing headlands here in South Africa, here in Brazil. There are lots of them in both of those countries, as you see here in Jericoacoara in Brazil. They quite often climb extensive terrain. So there's several examples on the Veracruz coast, for example, in Mexico. And here in northwestern Australia, where you've got transgressive dunefield and mixed parabolics climbing up a fairly big cliff and then forming cliff top transgressive dunefields. And of course, those are very, very common, excuse me, in arid environments where we have very minimal vegetation growth. So we see lots of transgressive dunefields in arid environments and climbing in cliff top systems, such as you see here in Western Sahara, and some examples from just where I was working in 2019 in Western Sahara. Beautiful transgressive dunefields, climbing dune systems as ramps, and then headland and clifftop dunefields. And of course, we have those relic systems throughout the world as well. Tons of them in South Australia, but lots in New Zealand. Here's a 120-meter high cliff, and this transgressive dunefield here, now fully vegetated, is a relic transgressive dunefield formed at former times, as we'll see later. Just bear in mind that often it's difficult to separate exactly when they're parabolics and when they're transgressive dunefields, and we often see them mixed together. A classic example is Mozambique, where you have these transgressive dunefield elements here and here, but lots of parabolics interspersed amongst them, both large and small. The fact is there's been very few studies conducted on transgressive dunefield barriers anywhere in the world, and probably most of the studies have actually been done in New South Wales by Bruce Thom, Peter Roy in the past, and there's very, very few people working on these things in general. So we don't know much about them, despite the fact that they dominate many of the south coasts and west coasts of various continents. So the big question is how are they formed? And here's a list of 8 ways in which they're formed, which I'm not going to read out here, but basically I'm going to go through quickly to give you a kind of idea of how I think they may form. In many cases, as you'll discover at the end of this talk, we don't really know if many or any of these are completely true in terms of how transgressive dunefields are formed. So one of the ways, of course, is sea level rise and transgression, and there are indications from some of the few studies that have been done, particularly drilling and dating studies, such as this one from Bruce Thom and associates from the Mile Lakes area, where you see that the oldest remnants of a now eroded transgressive dunefield or large parabolic system was actually forming as sea level was rising during the last postglacial transgression. So from about 10,000 years ago or so, sea level is rising from -20, -30 meters. As it's doing so, it's destabilizing the shoreline, pumping sediment onshore or both, and you get the first phases of transgressive dunefield development associated with sea level rise. So we see that as a significant trigger for a lot of these clifftop dune systems that are now stranded above cliffs or above present sea level. This dune system started forming 10,000 years ago when the sea level was -30 out here on the New Zealand coast, piled up against this marine terrace, formed large ramps, and then piled up onto the top. So there's reasonable evidence that that occurs, and certainly South Australia has many fantastic climbing and clifftop dune systems that date from that period through to the present, with still a few active ones in some places, as you see here in South Australia. And of course, another example is the Seal Rocks example in the northern end of Mile Lakes embayment, where we have this massive transgressive dunefield system in multiple phases and ages. But if you look at Bruce Thom's early work on dating this, the earliest phases are at least 4,000 to 6,000 years old or so, several kilometers inland, massive amounts of sediment pouring in here. So likely initiated at least when sea level is rising in the last 20 odd meters or so, or once it's got to roughly the present position plus or minus a meter. Okay, so that's certainly probably a decent trigger for, of course, lots of our barrier systems, including foredune plains, etc. The second way is that it would appear that just if you have a high sediment supply, you don't need much else in order to make a transgressive dunefield system. And so lots of places where we do not see any other dune types but transgressive dunefields right to the beach, such as here in POE, in Brazil, and many other places in the world, it would appear that if you just have enough sediment pumping on shore and winds blowing it across shore or alongshore or obliquely, then you make a transgressive dunefield by that means. And lots of examples in Brazil, for example, where we see this with sediment piling on shore, going landwards over older terrain or interglacial barriers and forming these large transgressive dunefields. Lots of the west coast of the USA has some of these big transgressive dunefields. Similarly, in the Gulf of Mexico, here in Veracruz, for example, and of course the Brazilian coast has dozens and dozens of examples, hundreds of kilometers of them. Here in the prograding coast, each one of those units separated by a small precipitation ridge here is in 1, 2, 3, are individual phases of transgressive dunefield development and stabilization. And these things are just stacking seawards as the beach progrades. But we also see that on the eroding coasts of southern Rio Grande do Sul as well, where you have a phase here, another phase here, and another phase here. But in this case, highly eroding coast and all active at the present time. But again, building on both eroding coasts and accreting coasts and stable coasts, just with large scale sediment supply. And of course, Lots of examples in southwest and Western Australia, New Zealand in the roaring 40s, and as I said, in Northern California. And we see, for example, when you look at 1870 survey charts that Andrea Pickard and I looked at for this paper, that they actually very well map transgressive dunefields right against the beach. Here's the 1870 survey, and we can match up points on the 1939 to 42 aerial photography. There's no foredune here in the 20s at all. Basically, this is just sediment pouring on shore, building a transgressive dunefield, we think, mostly. And of course, if the dominant wind regime is alongshore, then it's extremely difficult for vegetation growing along the backshore here to actually survive as the dunes are moving alongshore. So, you know, you get a greater likelihood of transgressive dunefield development in this case, purely because as the dunes advance alongshore, it's smothering and killing any vegetation that might be trying to grow along the backshore in form of foredune or another dune type. So, you know, easily formed, of course, on arid coasts due to the lack of rainfall, low vegetation cover. So this is part of Guerrero Negro. You know, here's a Google Earth image, massive amounts of sand in this huge sediment trap, which is at the bottom of the California system, pouring on shore, building wave after wave or phase after phase of transgressive dunefields over time. A few vegetation and nebca, you know, isolated little dunes formed in plants sitting here, but massive amounts of sediment just pouring on shore in this case. And of course, the Namib Sand Sea, you know, this is a mix of coastal dunes and desert dunes all together. Again, hyper-arid, very little chance for vegetation to grow. Similarly, in lots of the arid countries in the rest of the world, for example, this example in Yemen, where we have these beautiful climbing dunes, locally high sediment supply on a hyper-arid coast, building nice transgressive dunefields. And of course, in South Australia, we have probably the largest cool water carbonate factory in the world out here, still making tons of sediment, piles of that sediment pouring on shore, dominated by nebca type foredunes, lots of gaps between, and sediment still pouring on shore in the current environment. And here's another example from Morocco. And, you know, one of the big dune fields in the West Australia, South Australian border region, where you see just massive amounts of sediment still pouring on shore by this means. So, you know, probably no doubt, but almost no detailed work done on how much is coming on shore. Is it still coming on shore in most places? But probably no doubt that sediment supply alone is a big factor. Of course, you need reasonably moderate to high wave energy to drive that sediment on shore. The next way is via climate change, particularly changes in storminess, you know, reduction in rainfall, increased winds, development of an arid phase. There is a nice paper by Matthew and Davidson Arnott and Olahead, which shows a very nice causal link between a single catastrophic storm, complete destruction of this dunefield, and creation of a new transgressive dunefield post-1936. So this parabolic dune complex here, most of the Dunefield in here, and this is a precipitation ridge, you know, the back slip face ridge of a small transgressive Dunefield, and these dark areas are now water bodies and wetlands which were deflation plains. This entire system was created after a single massive catastrophic storm in 1936, which destroyed everything that was there before. Very good evidence for this. And these Dunefields developed after that. So, you know, there is one example of a massive storm creating a new transgressive dunefield system, but very few other examples. We have observed that dunefields get vegetated due to decreasing winds and increasing rainfall over time, as this example in Florianopolis and Mozambique Beach in Santa Catarina in Brazil, where Graziella Miotta da Silva did a lot of work. And you see here the Dunefield in 38, largely vegetated except for the big transgressive Dunefield lobe at the end here, with a 70% increase in vegetation cover by 2002, principally because of decreasing winds and the combination of increasing rainfall. So, you know, climate change primarily. Presumably the reverse occurs, but we actually have extremely little data or observations to show that. And of course, there's big hysteresis in these systems. So once I largely vegetate the system, it takes a hell of a lot more increase in winds and decrease in rainfall, I think, to actually turn it back into a transgressive Doomfield or start a new phase. And so it's interesting that, in the desert and semi-arid, arid literature, there's lots of research on that climate changes drive Doomfield changes, the creation of blowouts and parabolics, and the decrease the vegetation cover. But we don't see much of that work or evidence in coastal Dunefields. Of course, in coastal Dunefields, we have the added problem of shoreline erosion, salt spray, various levels of hysteresis that may not exist in deserts. This is just an example from one of the parabolic Dunefields I'm working in China. So then number 4, or 4A, is coalescence of parabolic dunes. I look at this picture of Andy Short's and go, well, maybe those were parabolic dunes once, which expanded laterally as they expanded downwind, and the trailing ridges were slowly destroyed and broke down, and the parabolic dunes are joining up together to make a transgressive Doomfield. Maybe. Certainly there is a little bit of evidence that parabolic dunes will end up as transgressive sand sheets or Dunefields. So this example from the Zeitdorf Cliffs in Western Australia that are about 118, 120 meters high. And if we look at a Google image from 2005 here, keep your eye on this arrow here, which just indicates the same spot. You kind of have either a fat parabolic dune or a small, transgressive Dunefield, some other parabolics here. And by 2015, so 10 years later, lots of those have merged together and expanded considerably if you look at the arrow. And so, now we could regard this as either a mixed parabolic transgressive Doomfield or a transgressive Doomfield. There isn't a great deal of shoreline erosion here, but of course no one's done the detailed work to figure that out. Foredune destabilization and collapse is one of the things that's very common in the literature, and I've been guilty of saying this in the past. Andy Short and I in the past said, foredunes collapse and they build new transgressive Dunefields with absolutely no evidence whatsoever, but good subjective science. And so we can imagine where we see foredunes like this, or foredune blowout complexes that slowly get more erosional over time, and they start to break down, and then sediment flows through these systems, particularly through the blowouts, but through the gaps that are created into the backshore region here and into the area behind the foredune. And as the foredune breaks down, we start to see destabilization, collapse, and the initiation of a new transgressive Doomfield phase. A recent paper reviewing some of this by Derek Jackson and Susanna Costas has that kind of model which several previous studies suggest, but again, there's very little evidence. So at the start of this, you've got a Dunefield and foredunes. You start to erode the foredunes here and the beach recedes. Blowouts start to develop, parabolic dunes start to develop, and you end up with a transgressive Doomfield phase. This is very commonly suggested throughout the last 60, 70 years of literature, but there's in fact, as we'll see, very few real examples of it. And I think there's a tendency to look at a picture like this from the Landwehr Dunefield. This is this Dunefield many years later, and look at the foredunes sitting across the front here, the deflation plane, the transgressive Doomfield behind, and go, oh, in order to make a new one, you have to break down this foredune to make a new transgressive Doomfield phase. But we know, for example, that in the 1900s to 1940s, there was virtually no foredune along here. There were a few isolated mounds or clumps of plants. W.S. Cooper's diaries along this area in the 1920s says there's no foredune at all. So there's a tendency for us to look at these in a certain evolutionary stage where they have a foredune or they look like this and go, you need to break down the foredune to make the transgressive Doomfield phase. I'm not so certain about that anymore. So that, if you look here, a very young transgressive sand sheet or Doomfield phase just starting out and a bit more evolved here. Foredunes redeveloped along the front, but it might be possible to destroy the foredune, as we'll see a bit later, and not actually make a transgressive Doomfield phase at all. It may be that you have a new slug of sediment coming in to make it. So, we tend to assume that the foredune needs to break down to make it. There are a few examples in the world where that's actually happened. Number 6 is topographic acceleration over cliff tops and perhaps high foredunes. There's a theory that if you have a 20-meter high foredune, you're going to have significant shear over the top, and it's hard to find a foredune in the world that's a natural one that's above 15 to 20 meters high. So maybe the wind velocity shearing over the top there gets to a point where actually it's virtually impossible to grow much higher, maybe. This is some computational fluid dynamics modeling of scarp flow, the incident winds coming this way. You know, the blue is very low velocity. We have flow separation and recirculation in here, and similarly flow separation over the top of the white cliff here with flow separation here. But at around that cliff edge, there's extraordinarily high topographic acceleration and high velocities, and that easily leads to destabilization of dunes if you've got them sitting here. Prandtl, of course, had beautiful smoke flow experiments showing this from the 1920s with the incident wind here, flow separation here, streamline compression and acceleration over the top of this little element here, flow separation here. So very high velocities in this point. And with or without erosion of the cliff here, it's very easy to stabilize those dunes along the crest there because of these very high velocities. You know, it's hard for plants to grow. Add that to high sand transport and high salt spray loads, and you can destabilize these dunes and make a dune field phase by that process. And you see another example here, I imagine from Espriu in Spain, where if we zoom in there, you see significant cliff top erosion and the creation of a new sand sheet phase in this older Dunefield here. Of course, it helps if you're eroding the scarp back in terms of destabilization. So it may be that it's principally shoreline erosion, but after all, you still get very high velocities along this crest line. So it's possible. Number 7 is water table fall, vegetation dieback, and foredune or Dunefield collapse if there's no foredune. So Uli Seeliger and his colleagues documented the decline of a coastal water table in southern Brazil due primarily to pine plantation in the back of this Dunefield, where the pines just started sucking the water out of the groundwater, which is quite shallow here. You can see all of this wet stuff here in the Google image, and basically led to the initiation of the transgressive Dunefield. You can see that at the time when this photo was taken, the foredune is actually fairly poorly vegetated. It's really sort of sand sheet and nebka together, as you see the blown up example here from 2003 to here. But, you know, it's 30 to 50% vegetation cover, just depending when you're on the ground. There's a house here for position, and this is 2003, 100-meter scale here, and this is 2010. And unfortunately, we don't have much imagery in between. But this is a modern example, or a more modern example of what Uli saw in the 90s. And basically you go from, you know, a poorly to moderately vegetated foredune, an older, small, transgressive sand sheets or dune fields here, to this massive wide sheet of sand, just barreling landwards and wiping everything out almost back to the house. In fact, the house is now fully covered in sand. This could be another event where we've seen the water table collapse, the plants die. It has to happen very rapidly, of course, for the plants not to be able to keep up with a slowly declining water table. And so definitely possible that this can happen due to collapse of the water table. And then there's fire. And of course, Southern Australia and Fraser Island have seen some magnificent examples of fire on Dunefields in the last year or so. So the one on Fraser Island, of course, lots of New South Wales, and the ones on Kangaroo Island. And Filion in 1984 published a paper in Nature where she was looking at Hudson Bay here in Canada and looking at these transgressive Dunefields and how they were formed particularly by fires. And she's right up at the outer forest limit here. And she argued that the fire frequency here is high. Post-fire vegetation colonization is likely to occur in warm periods, but it's actually compromised during cool periods because those periods are also drier. So she argued that you go through this cooling period, but which is also dry. You have a fire, you have a delay in post-fire colonization because of the dryness and a lack of humidity. That creates aeolian activity and a new Dunefield phase. And then when it starts to warm with increasing humidity, you go towards a dune stabilization phase. And she had, in some of these Dunefields, she had about 1 meter of sand sitting over charcoal layers, perhaps indicating that you've had fires, and then if you also have this dry period, you would create a new Dunefield phase. Well, we have an excellent example, of course, in Kangaroo Island with the fires of January 2020 to look at what the effects might be from these fires. And most of this I'm now reporting is work by Graziella Miotta Silva and my PhD student, Marcio da Silva. And here's a part of Kangaroo Island showing where it's all entirely burnt. And Marcio's looking at 3 sites here. So Maupertuis Bay sitting out here, and the next one, Snake Lagoon, sitting in the back, and then Hanson Bay here. So Snake Lagoon here, which is in the back of this Dunefield, several kilometers inland, transgressive Doomfield and mixed parabolic dunes, as you see here. And Hanson Bay, all of these places widely burnt. Remember, the fire temperatures were up to 900 degrees C, and other authors have argued that these are the most intense fires ever experienced in this part of the landscape. So, you know, if we were going to see a new Dunefield phase develop in these very high windy, you know, summer dry environments, you might expect that it would happen here. In fact, what we see post-fire is lots of sheet wash and gullying and rain wash and removal of the first few centimeters of sand off the surface of these high dunes. Remember, we're looking at ridges up to 50-meter high with 30-degree slopes. So, you know, you would expect to see a reasonable amount of wind erosion in these environments. In fact, we see gullying in the interfluves and some sheet development, but lots of small sheets and gullying and mostly sheet wash off these slopes, down to this massive intense root layer, because a lot of these dunes are covered in mallee. And the root layer is so intense that once you take off the first few centimeters, you tend not to be losing anything else. And if you dig some holes down on the bottom of some of these interflues, you basically see the charcoal layer. This is an older paleosol here with fine, clean sand, post-fire sand on the top. Our best guess is that all of this is sheet wash delivered sand and deposits, and a little bit from this gullying and fan development, but virtually no aeolian in this environment. So essentially what you're seeing when you look across that landscape is that sand has been removed off the crests and the upper and middle slopes, and that yellowy sand you see there is the stuff that's been removed by sheet wash and deposited all around the bottom of the slopes and in the interfluves and valleys in between the dunes. Again, here, this yellowy stuff is material that's been washed off here and down under here, but we're actually not seeing much aeolian action at all. And of course, as you see here, this is 6 months after the fire. The vegetation is certainly starting to come back wholesale in this environment. Of course, less on the crests because it's much drier. But we are certainly not seeing in this environment fire producing a new Dunefield phase by any means. And so, you know, when you look at that, you might say, well, the stratigraphic record that Filion and others have been interpreting as charcoal, then clean sand, means the fire created a new transgressive Doomfield phase. Perhaps, perhaps not. But of course, it might depend on the vegetation community present. She was looking right at the northern limit of tundra forest. And of course, she also had these climate periods which were much drier. And in fact, of course, in the period that we saw post-fire, we had a fairly lousy summer. It was relatively wet and it wasn't particularly windy or dry. So that might make the difference. Number 9 is shoreline erosion. And I've sort of mentioned this a bit before, but looking at it in more detail, there are places like the Lachenal Peninsula in just south of Perth that's eroding at about 1 metre per year. And you assume that this parabolic dune, transgressive Dunefield system is being forced by foredune destruction and barrier rollover and dune transgression due to this 1 meter shoreline erosion rate. Of course, we don't know that for sure, but that's what it kind of looks like. If we look at other examples from around the world, just one example here by Bresselier from the Grand Dune de Pilar, the highest dune in Europe, 10,000 to 3,500 ago, was way out here because the estuary of Arcachon changed its path considerably, started eroding into the shoreline. We make a small, transgressive dune ridge, and slowly over time it builds upwards and landwards and makes this magnificent, narrow but high transgressive dunefield by shoreline erosion effectively. So we've been looking in South Australia for examples of where we might see this happening, and of course the Younghusband Peninsula is the longest barrier lagoon system in Australia. It's about 190 kilometres long here with the Coorong Lagoon behind. There's a place called 42 Mile Crossing here, which was named, back in the 50s. So 0 miles is down here and 190 is at the top end. And just along this barrier system, which has completely changed from being large-scale transgressive dunefields mostly in the 1940s to significantly vegetated now, particularly once we got rid of the rabbits. Then there's a place called just south of 42 Mile that we call 41.5 for the sake of it. And if you look at the air photo coverage over time, this is 1967 photo and 1995. Basically in that period, we saw the entire removal of a 60-meter wide foredune due to shoreline erosion at that time. And then this is aerial photography from after that occurred, from 78 to 2019. And what it shows is that as you continued with shoreline erosion over time, and these photos, air photos, are lined up such that they're all geographically in the same space. So you're seeing more surf zone in this 2019 image because they're all in the same georectified space. And what you see is as the scarp gets cut back and the shoreline retreats, we see the scarp crest slowly coming unstuck, starting to be less and less vegetated. And by around 2013, we start to form a transgressive sheet, and that's quite significant by 2021. And just to flick through a couple of images for you, this is 2005 and 2007, and we've got erosion rates of about 2.55 meters per year. By 2015, you can see it's well developed now to the high scarp and even better developed by recent times. 2018, for example, erosion rates been up to 7 meters per year. The erosion rate's 5.1 meters per year. The downwind migration rate or extension rate of the transgressive sand sheet about 7 meters per year. And here's aerial and satellite imagery georectified together. So the poor quality of these is because they're blowing up satellite imagery, but it shows you every year from about 2011, and you see somewhere between 2011, 2012, we start to see that scarp cutting back, destabilization of the crest, and the eventual development of this transgressive sand sheet, which is fairly rapidly developing into a dune field. Here's 2008 LiDAR compared to 2018 LiDAR. There's the shoreline or the dune toe from 2008, just to give you, an idea of the changes. And here a little cartoon or video showing you that change over time. So 2008 LiDAR merging into 2018 LiDAR. You can see massive change as this scarp becomes the primary scarp face or the dune toe. We see, large scale destabilization and cannibalization of that dune scarp and transfer landwards into a new transgressive dune phase. So, scarping, scarp collapse, blowouts develop particularly up in the top of the scarp. It's about 15, 18 meters high here. The blowouts enlarge, as we see here. The slope retreats via aeolian erosion and cannibalization of the relic dunefield that it's now sitting against. So the slope goes from relatively vertical and slowly gets cannibalized to a lower slope. So sediment's primarily coming off here and going landwards. And as the slope retreats, we don't think there's any supply from the beach at all. It doesn't have enough time to recover from each erosion event. Some blowouts become parabolic dunes, but most disappear as the slope retreats and the Dunefield expands. And here's just some recent photos from 2020 showing you the front of the Dunefield, and this is looking along the precipitation or slip face ridge at the back. So it's becoming quite extensive. Lots of these nebca on the top are either bits of plants that survived as the Dunefields created, or new nebca forming on the top of the sand sheet as it develops. And here's just two drone DEMs showing April 2020, February 21, downwind expansion rates about 7 meters per year at the moment of the Dunefield. So again, this is further research of Marcio de Silva's that we're developing at the moment, that he's developing at the moment. But you can see clear, unequivocal evidence really of shoreline retreat, shoreline erosion, and the development of a new transgressive dune sheet, or transgressive aeolian sheet and incipient Dunefield by this process. So in conclusion, there's a bunch of theories and hypotheses on transgressive sheet and Dunefield initiation, but actually, there's not a great deal of proof for many of them. As you saw through this talk, I've kind of indicated where we think things lie, where we think we see evidence, but we don't have a lot of evidence, in fact. Certainly, large sediment supply on high energy beaches, moderate to large sediment supply on arid beaches, water table collapse, and a single catastrophic storm, reasonably established triggers, but a whole lot more research required, particularly on these large sediment supply on high energy beaches. What exactly is the role of sediment supply versus wave-driven sediment supply, etc. And lastly, of course, the new research on the Younghusband Peninsula by Marcio establishes pretty much beyond doubt that shoreline erosion combined with the cannibalization of high scarps can initiate a new sheet Doomfield phase. But note, we completely eroded a 60-meter wide, 5-6 meter high foredune. We didn't make a transgressive Doomfield by that process. We only made it once we had a high scarp and started to cannibalize the scarp and the relic dunes. Thanks very much.
Thanks a lot, Patrick. Perfect timing. So there's plenty of time for questions for Patrick. So either